Okay, so looking at yeah, let's continue. So I was what? Search this data set. Doesn't the ID work? If I search for this ID, should actually find it, shouldn't it? What? Oh, there you go. No, what? This one? Yeah, this. What happened here? Because I wanted to get that notion, so I might want to actually put the. I think I'm gonna put in here the row, because I think the one of the problems is I'm not so sure it's not so good at. Well, at least I'm struggling when it comes to the grok part here, to make sure that it's understanding the notation. So I know C sub 2, this is I think like a famous group. So but let's just go first. I want to go and understand that. So so I want to know, can you explain me what this notation is? As the square of a cyclic group C2 itself. Okay, so I mean here it seems like, so okay, but what does it mean what does it mean when you do like squares or dot products of groups? So C2 is the cyclic group of order 2. The smallest non-trivial group is generated by a single element A, cyclic group with relations A squared equals E, where E is the identity. Explicitly it says E and A, and it's abelian commutative. This group is isomorphic to, so integers modulo 2 under addition. I think that's not valid, because that's just, in this case, it's just we're defining D, so it's not D. What does it mean? What does it mean to, or what's the interpretation of the dark product of a group of two groups? So nice. Yeah. The dark part of two groups is the way to construct a new group by combining their structures component-wise. Okay, so it's just the it's kind of analog to what a multiplication of a tensor would do, or a matrix, right? So the set of all ordered pairs. So if G is, yeah, so if G is an element of G and H is an element of big H, then it's basically all the elements of the new. Okay, cool. Yeah. The inverses, the identity. Okay, so multiplying is just creating a new group. So in particular, in this case, we're multiplying C2 with itself. And all right, fine, whatever that means, right? So it's a definition of D, this is the definition of S. And now we're defining G as whatever that is, and that's going to be the interesting aspect of these. Let's see, we're in this question. R times. Cool. Now help me interpret these par. These. So this might be another way of combining those, I guess. This might be a new way of combining those. It's a semi-direct product. Okay, interesting. So of D and S with D. No, D is not declined. Whatever group, it's fine. It's fine. Stop. It's the semi-direct product. So it's the semi-direct product. So what's the semi-direct product of two groups? N and H. It's that's correct. It's denoted like these. Okay, so they're using the X, but like it has like a stripe, so it's a semi-product. And here we've got the same part of D and S, and it's probably going to be something where it's the product by with just some extra or limited in terms of certain properties. To specify the action is a way to construct a new group G that combines N and H, where N is a normal subgroup of G. H is a subgroup. What? And their intersection is trivial. I don't get it. So it's a way to construct a new group G that combines N and H, where N is a normal. It's an extension of the direct product. Okay, it's an extension, but with it, so it's the direct product with a twist. The elements of H act on N via automorphisms. Okay, this is actually interesting. Allowing non-trivial interactions. Let's go into these. Okay, so what are automorphisms in this context? What are? Oh well, it's here. So the problem is, I think those sometimes are just a little too formal for my taste, at least for what I'm trying to do now, but it's good. So to form N, how do you read that? How do you read that? R times. I'm gonna say R times. And R times H. You need a homomorphism. No, automorphism group of N. So this thing, like I think that's a phi or something like that, defines how H acts on N by conjugation in the larger group. Okay, so we need to understand that a bit more, because this is then tied. That's where action here. So this is tied to what action means in here, right? That's what I thought initially was something about like physics or something, but it's an action of of S on D is induced by the only possible non-trivial action. Induced. I don't know what induced means in this context, but okay. So we're defining two groups, whatever those two groups in terms of properties have. And again, we don't have to try to find a meaning to this, but we need to try to find, like, we need to try to get to 5, but I would like to understand why Grok thought it was 1. Because if I scroll all the way up, no, sorry. If I scroll all the way up, it thought for 13 minutes and it got to the answer of 1. And it will be interesting to read these. Because it does try to do something, computing conjugacy classes, calculating two regular classes, exploring smash product structure. Searching for theorems. So let's look up theorems and block counting for groups with normal. So it actually does. It's a lot of thinking. I think based on what I'm so it's a normal subgroup and group actions. But let's keep exploring that. Okay, so we need to understand now. We need to understand more, and I think I'm gonna stop here. I'm not gonna dig more into the question. I want to understand groups and actions a little bit better, and maybe I'll start a separate conversation in this project, and I wanna learn more about groups and actions on groups as in the context of in the context of um, mm, 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 an R product in Dart product between two groups. So write things down so they are easy to approach by someone who's not too deep in the group here. Let's see what it does. I'm gonna mute myself for a second. Let's go. Okay, so let's start from the basics. What a group is. So algebra group is like a set of things where you can combine them in order to follow some rules. Yeah, I mean, maybe that was a little bit too. Think of it as a club with members in operation, like addition or multiplication that lets you pair any two members to get another member. And the key rules, actions for group operations, closure, associability, inverses, all fine. We can skip that. What are group actions? Group action is a way one group operates on or moves around another set or group. It's like the first group is giving instructions to rearrange things on the second. Interesting. Formally, if G is a group and X is a set, are we dealing with groups? And I mean, let S and let D. I mean, those. I assume those things are just groups. An action of G on X is a function that assigns. Okay, that's what I was looking for. So, if G is a group and X is a set, G is a group and X is a set. An action of G, the group is acting on a set. I guess the set is a group without an operation, right? That's my guess. An action of G on X is a function that assigns to each G in G an X in X. It's a mapping, basically. It's a function. So a new GX in X. An action of G on X is a function that assigns to each G in G an X in X. A new GX in X following. So actions compose. Okay, so identity acts as do nothing. If X is itself a group, we often want the action to respect H's structure. That means the action is via automorphisms of H. Whoa. Each G in G gives a way to twist H while preserving its group operation. In other words, for each G, there's a homomorphism that is invertible. There's a lot to unpack here. So imagine G as rotations, like a clock hand group. Acting on H as positions on a circle by rotating them. So G would be the group. So a group is basically then the symmetries, right? For example, symmetries of score, whatever it is. Like it's yeah, it's kind of like it's elements and actions, and and what you're doing with an action is of a group on a set, or a group on a group, is you're transforming those elements of that group while respecting the structure of the group, so while respecting the operation of that group. I was gonna say, isn't product, so when you have two groups, because that's kind of what I was thinking, that is something that isn't that just like, isn't then the action seems to just be the definition of the of that product, right? So when you have two groups N and H, you can combine them into a bigger group. There are different ways. You can do a direct product. It's a straightforward way. So you pair elements and you multiply component wise. So there's no interaction between N and H. They're independent. There's like two separate clocks ticking without affecting each other. Those examples are not the best, I think. Semi-direct product. This is an indirect product. This is the indirect product you mentioned. Semi-direct. I believe our product refers to a semi-direct product, often denoted with E is indirect product because it's not direct. H acts on N. Okay, that's why they call it an indirect product, right? Because it's not, you're not directly combining the elements, you're just defining how one affects the other. So N, in this case, H acts on N. So the group that is on this funky side that has the closed edge is the one acting on N via a group action, specifically a homomorphism from H to the automorphisms of N. So let's try to unpack what a so in this context, what is an automorphism? It's got to do with the actions and transformations, I think, but I just want to be more formal. So let G and H be groups with respective operations, often just written clear from context. A homomorphism from G to H is a function G to H that preserves the group operation. Okay, so a homomorphism. Meaning that this function of, oh, it's actually a function that relates then. It's an action that is using, okay, that actually helps. This actually helps. This means, okay, let's try to process this. This means that this function applied to a combination of elements, although I struggle because they're using here the G product, and how can you, oh yeah, okay, so A and B belong to G. Okay, that's all good. So it's mapping the operations. It's actually mapping the operations. It's mapping, it's a map of, it's a map that basically translates what the product of G means. It tells us how to interpret, it tells us basically how to understand the product of H in the context of G. It's almost like saying, for example, and maybe that's not totally accurate, but it's like saying, okay, so how does addition work with the complex numbers, right? So how, like, you know, okay, so would that be, let me just verify that. So would a close analogy be like, how be like a homomorphism defines how addition in natural numbers would work with complex numbers. Right, so being natural numbers and complex numbers being two separate sets or groups, how we want to call them, groups, right, because they have elements and operations, I guess, and essentially the homomorphism is just a definition of like the plus, like the addition operation should, you know, behave like these, right, because it's basically saying this homomorphism is something that defines, you know, the if you take that input, like this would be the G would be the natural numbers, so it's like A plus B, and then what you need to change in A and what you need to change in B. I think so. I'm complex numbers. How should natural numbers work? Complex numbers. Does provide a way to embed or integrate the structure of one algebraic object like a group into another, preserving the operation. Your analogy is somewhat close, but needs refinement. As natural numbers under addition form a monoid, not a full group. Okay, since there are no inverse except for 0, while complex numbers are under addition do form a group. Let's break down the formula yet accessibly. So it maps elements from the source structure, N with addition, to the target structure, C with addition, such that the operation is preserved. In your terms, it defines how addition in natural numbers would work by translating it into addition in complex numbers. Yeah, okay, that's kind of what I meant, I think. Meaning, if you had two natural numbers and then map, it's the same as mapping them first and adding in C. Yeah, exactly. So it's like the same as saying like addition will work. Take a natural number, turn it into a complex number, do the addition, and yeah, it basically it's okay. I think it's fine. So that's what homomorphism is. So the homomorphism is mapping the operations. The automorphism of a group G is a homomorphism from G to itself that is also bijective. An isomorphism. In other words, it is an invertible function such that, yeah, but why is that relevant? The set of all automorphisms of G forms a group under composition. What the fuck? No idea. Okay, so that's fine. I mean, in the context of a semi-direct product, I guess what's trying to say is that the action of H on N is... Does this mean that the action of H on N becomes the operation of the new group? Let me step back here. Go back here. So the direct product, where was that? Relevance. Wasn't it here? Or was it here at the top? Groups, group actions, yeah, exactly. So group action is the way one group operates on another one. So it's like the first group is giving instructions to arrange things in the second. Products of group. So this is the indirect product you mentioned, I believe our product first. The action is just a way to define multiplication twists n using the action from h. More dynamic. Okay, so that's the reduction to the direct product. So so essentially, so there's an example here. Let n be whatever that is, which says integers mod 3 under addition. Let h be 0, 1 under addition. Action h acts on n by flipping when 1 in h, So 1 acts as a negation, mod 3. So 1, 2, 2, 1, 0, 0. What? Has 6 elements, right? The combinations of like 0, 0, 1, 0, 2, 0, 0, 1, exactly. Multiplication. H acts on n by flipping. Wrath product. Why care about these? Semi-direct products help classify groups. Many groups like are semi-direct products in most situations where one symmetry affects another, like in physics, rotation acting on translation or cryptography. Compute, okay, oh, so this practice. Compute multiplication tables for these with different actions. Okay, so I guess they're, okay, with different actions. Abstract algebra. No, that's good. I mean, that's actually good. That's actually pretty good. I think I got to a point where my understanding right now is that, and even looking at this example, that's just a choice, right? So essentially, essentially it's a way to construct things. So you're saying that we're defining this set, this group, and then we're constructing another group with an indirect product, and we're defining here an action of S on D this way, where the action of S on D is induced by the only possible non-trivial action of and then they're asking us, so we're building these, because I think the way that we can approach these without digging too much more into detail, I need to understand that part here, and I need to understand what this induction here means. Then I need to find a way to build these from with tooling. I don't know if to use something like SymPy or some. There's gonna be software that helps me do these, right? I don't want to do the groundwork of like doing this all by hand on paper. That's fine. I just want to be able to build these, but I understand what's going on, right? So I think I'm just missing that. Let's just take a little sneak peek into these, and then we'll move on. I'll just do 5 more minutes, I think. Section S and induced by the only possible non-trivial action. So what does it mean that an action is induced by another action? Is it just English, or if I say an unrelated question, if an exercise the problem states the following, what does induce in this context mean? Is this a specific concept? In group theory? Induced action, an action derived from another. Okay. So it does mean something. That's going to be difficult to unpack. Actually, I think we'll definitely need a few more sessions, because this is essentially saying S, so it's reusing the definition of S over this C3 squared, which apparently equals to C3. And C3 is, I think, a known group on D, but D is just C2 squared, right? So I guess what's basically, I think first we need to understand what is this only possible non-trivial action. No, by non-trivial, I guess it means that it's not the direct product, that it's you know, that is not the one that doesn't have any effect between this group and this group. So C3 and C2 squared. And then this is supposed to help us derive the action that we need to apply from S to D. And when we have these, then we can construct G. And when we have G, then we need to understand what the heck is a field with a characteristic 2, and what a blocks. There's a lot of. Anyway, whoa, that was actually a long answer. Derived, extended, or defined from another existing action. Homomorphism. Okay, yeah. So an induced action arises when a group action on one object, set, subgroup, or space, naturally gives rise to an action on a related object. Common ways this happens would include restriction to a subgroup. If a subgroup G acts on a set X, the induced action. So if a group G acts on a set X, the induced action on a subgroup H of G is simply the restriction of the original action. Okay, that's what it means. So this is good. So essentially, we need to find first what the action, what the only possible non-trivial action of C3 on C2 squared is. That's step number 1 to approach the problem. This is kind of the, you know, kind of need to hunt for these, right? So where do we even start attacking the problem? So that's the first thing, is to try to understand. Take these. But I mean, if it's telling us that this is equal to C3, then I'm going to just say C3, and like the only possible non-trivial action of C3 on C2 squared. Does Grok know this? What's the non-trivial action off on C2 squared? Does it know this? The thing is, I might I also want to check if what tools could we I don't know what out is in here. So the non-trivial action of C3 on C2 squared is given by a faithful homomorphism Okay, so we will want to focus on that subproblem first. We definitely want to focus on that subproblem first, and then try to understand, because we need that action of S on D, and if it's supposed to be induced, yeah, well, first we need to understand why is this equals to C3. Yeah, all good, cool. We'll figure it out, but I think we've unpacked quite a lot today. We've unpacked quite a lot. Cool. See you in the next video.